Can you settle an argument with math?
Previously on Figure It Out, we wanted to settle an argument between management, Bob and Linda, and the labor, the kids. The changes to the job are a $1 per hour raise for the labor, D, a weekend day off for the labor, SQ, which stands for status quo, which means no changes from last year, C, management hires a cleaning service and eliminates one job, and B, management wants to eliminate the 15-minute break due to labor abusing it. The normalized utilities, or numerical values, have been assigned to each of these changes. We will notice that the status quo has a value of 0 for both labor and management. The values will create a set of coordinates, which we can use to graph a region in which the solution can be found. So again, looking at the utilities a little more closely, here we see that management values a raise of -3, day off valued at -2, status quo valued at 0, and the cleaning service option with the eliminating a 15-minute break both coming in at a 4. Collecting the values for each, the management and the labor, as an ordered pair, we can create a set of coordinate points, which when we graph, we will find a solution within a region on this graph contained within the points. So to see this, let's take a look at what this looks like when we do in fact graph all of the possibilities. Now there are 16 possibilities that we can combine each of these with. So normalized utilities have been assigned to each of these changes, and when we start putting together the combinations, we have an additive value for the individual pieces since each individual change is independent of the other one. So here is a list of the 16 possible values or coordinates to consider for the graph. Working at the details of these values, we get all a set of 16 coordinates. So for example, a combination of points C and B is additive for each component. 4 plus 4 gives us 8, -2 plus -1 gives us -3, and so on. So using each individual coordinate, we can get the combinations of the different coordinates and plot them on our graph. Next, once we plot all of these coordinates on the graph, we will enclose it with the smallest convex polygon that will contain all of these points. So a convex polygon means that all the corners of the polygon are pointing outward. All right, and so when we have all of these coordinates, we have to be very careful when we build this polygon so that we do contain, in fact, all of the coordinates. All right, so we're going to see what this graph looks like in a moment. The payoff polygon, again, is the smallest convex polygon that contains all of the points. Looks like this, and it's not very pretty. But you can see that the boundary in green has some of the points on it and contains a region of area that has the rest of the points in it. Now, according to the Nash equilibrium or Nash arbitration scheme, which focuses on the solution being on the northeast boundary of this polygon, here I've labeled those boundary lines as Y1 and Y2, highlighted in blue and green. Okay, so we'll be looking for a point that satisfies this Nash arbitration scheme, as discussed in our last video. And if you recall, the equation of a line is given of the form y equals mx plus b, where we can locate the slope by finding the rise over the run or the difference of the y's over the difference of the x values in our coordinate system. So the equations for the boundary we get for the y1 is -1/2 x plus 7/2, and that'll be within the interval from 0 to 3, keeping us within the first quadrant. y2 is -x plus 5, and that's going to be on the interval from 3 to 5, again keeping us within the first quadrant. So the boundary has been highlighted on the graph there, and the equations that go along with those boundaries are now going to be substituted into the product equation. So the product is x times y, and the y part is the y1 or the y2, respectively. So in order to find the maximum value of the product f of x equals xy, we differentiate the product once we have substituted the respective expressions in for y1 and y2. We then look to find the critical points of that product. So setting the first derivative equal to 0 allows us to find the critical points x equals 3.5 and x equals 2.5 for the f1 and f2 product equations. And we find that neither of these values fall within the intervals of interest. So we are just going to have to check the endpoints of the intervals in this product. And as it seems, x equals 3 provides the largest product, which is a 6, so we're going to use the x value of 3 on the boundary equation to get the Nash equilibrium solution, n equals 3, 2. And that means that a choice of hiring a cleaning service, firing Gene, eliminating a 15-minute break, giving the kids a raise, and a weekend day off is the optimal solution here for Bob's Burgers.